Good afternoon. First of all, I want to thank Marcello, Florian, and Dario for inviting me to this interesting workshop and giving me the opportunity to present a talk entitled Chemical Complexity for Chemical Artificial Intelligence. In my presentation today, I want to answer three basic questions. First, why am I developing chemical AI? Second, what is chemical AI? And to answer these questions, I will also present a recent achievement that is a contribution to neuromorphic engineering in Wepper, and it refers to a biospire chemoacoustic system. And finally, I will answer the questions, what are the perspectives for chemical AI? Let's get started. Why am I developing chemical AI? Well, nowadays, humanity is prepared to face global challenges. A comprehensive and far-reaching list of these challenges is included in the 2030 agenda, compiled by the members of the United Nations 10 years ago. Reaching the goals of this agenda means dealing with human beings and their societies, the world economy, the urban areas, the natural ecosystems, and the climate. These systems are instances of what we call nowadays as complex systems. So it's evident that whenever we face global challenges, we need to deal with complex systems. However, we experience seemingly insurmountable hurdles whenever we deal with complex systems. And these hurdles give rise to the epistemological complexity. An hurdle is computational complexity. Many computational problems regarding complex systems are solvable but intractable. Examples are practical problems, for instance, scheduling or the traveling salesman problem, but also problems of basic science, for instance, the Schrödinger equation or the prediction of the three-dimensional structure for proteins. These problems are non-deterministic polynomial problems, and when they have large dimensions, we cannot determine their exact solutions in a reasonable time, even if we use the fastest supercomputers in the world. Another contribution to the epistemological complexity derives from the recognition of variable patterns that are emergent properties of complex systems. Although the research line focuses on the recognition of variable patterns is particularly lively, we still lack the formulation of a universally valid and effective algorithm for the recognition of every type of variable patterns. A promising research line to face the epistemological complexity is natural computing, an interdisciplinary research line, drawing inspiration from natural phenomena to propose new algorithms, new materials and architectures to compute, and new methods and models to understand complex systems, based on the rationale that any distinguishable physicochemical state of matter and energy can be used to encode information. And every natural transformation of these states is a kind of computation. Within natural computing, we distinguish two programs. In the first, scientists exploit the physicochemical laws to make computation by knowing that any physicochemical law describes a forward causal event, and any forward causal event can be conceived as a computation. Because the causes become the inputs, the effects become the outputs, and the law governing the transformation becomes the algorithm of the computation. In the second program, scientists mimicked information gathering and utilizing systems that belong to living beings. So we might mimic how cells compute, or how nervous systems, immune systems, and societies of agents compute. The research line of chemical artificial intelligence sprouts from natural computing, and is trying to answer the following heuristic question. Which biological intelligent competencies can be mimicked through inanimate chemical systems in water, in liquid solutions, which is the characteristic phase of life? Traditionally, artificial intelligence is developed through two strategies. One relies on software, running on current electronic computers or special purpose hardware. Such software either reproduces the human thinking process when it is a flow or rigorous logical operation, or it mimics some structural and functional features of neural networks to learn how to perform tasks from data, or it mimics some other natural rational phenomena, for instance, biological evolution. The other strategy relies on reverse engineering neurons and their networks in hardware for neuroprosthesis or to design pre-lie computing machines, revolutionizing the von Neumann architectures of current electronic computers. Recently, a brand new strategy to develop AI has been proposed. It's the so-called chemical AI that relies on molecules and macromolecules that operate as if they were hardware, but they are dissolved in liquid solutions where phenomena such as chemical reactions, diffusion, migration, advection, convection, and chemical waves can occur. And these phenomena operate as if they were software. In other words, the hardware and software of conventional AI are merged in the vector of reactive chemical solutions, maintaining out of equilibrium conditions. In this plot, I report a knowledge map of chemical AI, a three-dimensional graph projected on a plane. Along the x-axis, we have the Chi domains that are molecular and supramolecular chemistry, system chemistry, and multiscale chemistry. With multiscale chemistry, I refer to all those chemical systems that manifest self-organization at different spatial scales and multi-level causality when appropriate macroscopic thermodynamic forces are applied. Multiscale chemistry is needed to mimic some structural and functional performances of multicellular biological organisms, exhibiting multiscale competencies. In the knowledge map of Chi, along the y-axis, we have the Chi paradigms that are biosensors, biobrains, and effectors. And finally, in the third dimensions, represented by the saturation degree of the green color, we have the biological intelligent competencies that range from sensing to perceiving, from computing to planning, from working to acting. Some of these competencies have already been implemented chemically, and they are indicated in black. Some others have not implemented yet. They are indicated in white. Probably we require further development of system chemistry and multiscale chemistry to make these competencies be within reach. Or probably they cannot implement it chemically through the animate chemical system. Because if we think, well, between the competencies indicated in black and those written in white, we see that they are probably separated by a still unknown, unexplained concept, that of consciousness. An ambitious goal of chemical AI is the development of chemical robots. A chemical robot is envisioned as a confined complex molecular assembly that reacts autonomously to its environment because it has sensors collecting data about the environment and internal state of the robot. It has artificial neural networks processing the sensory data, making decisions, and triggering the actions of the effector models that can affect the surrounding environment. The intelligent activities of a chemical robot should be sustained by an appropriate metabolic model. Chemical robots should be easily miniaturized in order to be implanted in living beings and interplay with cells and organelles to perform biomedical actions. In other words, chemical robots should become auxiliary elements of our immune system. And in this case, the prototypes for chemical robots are the lymphocytes. But we might think of deploying chemical robots in the environment to fight pollution and face problems related to energy and food supplies, as enticingly alleged by the futurist Kurzweil. In this latter case, the prototypes for chemical robots become the microorganisms. The development of Chi might have a curious side effect. It will probably assist human efforts to unveil the mysterious event of the appearance of life on Earth. This staggering event has been described as a phase transition or sudden change from a completely abiotic world to a world where the first complex chemical systems capable of exploiting matter and energy to encode, collect, store, process, and send information to pursue goals somehow pop up. And now, after answering these two fundamental questions, why chemical AI and what is chemical AI, as I promised at the beginning, I'm going to present a recent achievement that is a contribution to neuromorphic engineering in vector, and it refers to a biospire chemacoustic system. In neuromorphic engineering in vector, we start from the idea that the computational power of any neuron relies on its dynamical properties. We exploit systems such as the Belousov-Zhabotinsky reaction, the orbital reaction, the hydrodynamic photochemical oscillator to mimic the dynamics of neurons in oscillatory, chaotic, and excitable regime. Then we put this system in communication through optical and chemical signals, and we detect spontaneous spatiotemporal synchronization phenomena analogous to those that occur in real neural networks. Some of these systems manifest the wonderful phenomenon of chemical waves that are autocatalytic reactions propagating through excitable media. This phenomenon is widespread in the human nervous system. Suffice to think about an action potential, that is an electrochemical wave propagating through, along the axon of a neuron for information transfer at the cellular level. Or we might think about the electrochemical waves propagating in the form of spindles in our cerebral cortex to consolidate and integrate memories during our sleep at the cerebral level. The Belousov-Zhabotinsky reaction, that is a catalyzed oxidative bromination of malonic acid in aqueous acidic solution, gives rise to outstanding examples of chemical waves, as we can see in this accelerated video. And since the behavior of the Bézier reaction is strongly affected by mixing, we explore the response of its chemical waves to mechanical oscillations. Here in this picture, I report the experimental setup. We pour a thin layer of the Bézier reaction on a polystyrene petri dish, and then we apply vertical sine mechanical vibration to the plate. And we found out that that device based on the Bézier reaction is sensitive to vertical mechanical vibration in the range 2010 Hz. So we propose that device as a biospire acoustic system capable of discriminating 7 acoustic bands included between the C note of the 7 octave deep down to the infrasound, as I'm going to show right now. First of all, I report the behavioral Ampere-Bézier reaction, where we detect spontaneous phase wave propagating from the periphery to the center of the dish and target patterns that can be either sparse or dense. What happens if we apply frequency in the range 2650? That means from the C note of the 7 octave up to the F note of the 5 octave. Well, we still detect spontaneous phase wave and target patterns, but the mechanical vibration make the front waves of the target patterns much more irregular. What happens if you apply frequency in the range 650-500? I always report the notes representing the extremes of these ranges. Well, we now detect a pacemaker of advection-induced phase wave in the center of the dish. And these advection-induced phase waves propagate anisotropically towards the periphery, generating clover-type shapes. In the periphery, we still detect the formation of spontaneous phase wave and irregular target patterns. What happens if we apply frequency in the range 500 to 100 Hz? We now detect a vibrating annulus in the middle of the dish. And advection-induced phase waves are generated in one point of this region. They propagate at first towards the center and finally slowly in the rest of the solution. What happens if you apply frequency in the range 295? We now detect 2 vibrating regions, one in the center and the other in the middle of the dish, in the periphery of the dish, separated by a steady nodal region. Advection-induced phase waves are generated in one point of the vibrating peripheral region, and then they move quickly towards the opposite side, engulfing the nodal region. What happens if we apply frequency in the range 9550? We now detect a Faraday pattern spread throughout the solution. That is a grid of cells generated through a parametric effect, through standing waves propagating perpendicularly with respect to the vertical vibration. The amplitudes of the oscillations are larger in the periphery rather than in the center, and advection-induced phase waves are generated in one point of the center of the dish, and they spread radially towards the periphery of the dish. What happens if you apply frequency in the range 50-15 Hz? The Faraday pattern is now uniform, and the dimensions of the cell increase by lowering the frequency, and advection-induced phase waves are generated in one point of the periphery of the dish, and they spread quickly towards the opposite side, sweeping the entire solution. And finally, what happens when we apply frequency in the range 15 Hz? Now the dimensions of the cell are so large to fragment the front waves of the advection-induced phase wave that appear irregular. The velocity of the advection-induced phase wave is apparently dependent on the acoustic frequency, as we can see in this plot. The lower the frequency, the faster propagation of the advection-induced phase wave. The interpretation of this dependence was possible by invoking the network of cells model. The solution of the busy reaction can be described as a grid of micrometric open reactors exchanging chemicals through diffusion and advection. The vertical mechanical vibration affect the chemical coupling among these open reactors. And the lower acoustic frequencies guarantee a more extended chemical coupling, the formation of larger clusters, and hence a faster propagation of the advection-induced phase waves. And the simulated values of the velocity are in agreement with the results, experimental results. The system is an instance of multi-scale chemistry because these spatiotemporal patterns we detect at the macroscopic level are due to the vertical vibration applied at the macroscopic level, the micrometric open reactors operating at the mesoscopic level, and of course, finally, the busy reaction occurring at the molecular level. Three are the key outputs for the discrimination of the 7 acoustic bands in the range 2010 Hz. First of all, the chemical waves, there are different types, and they have different acoustic frequencies depending on frequencies depending on the acoustic frequencies. In general, the frequency of the chemical waves are from 3 to 5 orders of magnitude smaller than the acoustic frequency. Then a second key output is the dependence of the advection-induced phase wave velocity on the acoustic frequency, described by this exponential function. And finally, the dependence of the Faraday wave's wavelength on the acoustic frequency. It means the dimensions of the cell constituting the grid, the Faraday pattern. Our biospire chemoacoustic system has some analogies with the human ear. First of all, in the human ear, the cochlea is a transducer of mechanical energy into electrochemical energy, and we have a tonotopic representation of the acoustic waves along the basilar membrane. In our biospire chemoacoustic system, the busy reaction is a transducer of mechanical energy into chemical energy, and we have peculiar spatiotemporal patterns that become a representation of different acoustic bandwidths. And finally, I want to conclude by presenting some perspectives for chemical AI that refers to the unconventional strategy for mimicking biological intelligence in welfare, which is the characteristic phase of life. The perspectives. First of all, chemical AI will promote the design of devices and formulation of algorithms to face epistemological complexity. Second, chemical AI and robotics will help humans face global challenges by mastering and colonize the molecular world. The colonization of the molecular world will provide tools to effectively combat poverty, clean up the environment, overcome diseases, and extend human longevity. Trying to obtain intelligent chemical system from scratch can help unveil two remarkable emergent properties of certain complex systems, such as intelligence and life. Finally, I want to acknowledge my current collaborators, my young resources, the European Union and my university for the financial support, and of course, all of you for your attention. You can follow me on the social media. And I invite you to contribute to a special issue on chemical AI open in this MADPI journal. Thank you for your attention.